So first of all, very good morning, all of you. I am Nitish Kumar, a PhD scholar in IIT Delhi in India. So this work is my PhD work. So in that, I'm going to present here the tunable piezoresistive NEMS pressure sensor simulation under various environmental conditions. So this is the outlining of my presentation. So first I start with the introduction. After that, I will device fabrication, simulation setup, result and discussion, conclusion, reflection, acknowledgement. So first start with the piezoresistivity. What is the piezoresistivity? Piezoresistivity is the just combination of the electrical and mechanical. So the change of resistance with respect to applied mechanical stress, that is the called piezoresistivity. So basically we take the one resistor near the cantilever fixed beam, because there we get the high strain on the resistance and during the apply the mechanical stress on the cantilever beam, and similar kind on in a diaphragm. So the silicon material have a inherent mechanical sensing mechanical property that shows the high sensitivity, because it's have a high gauge high Young modulus. So it's also excellent linearity for a sensing application. Further, some group also start the tuning of piezoresistivity to improve the piezo coefficient, like decrease the thickness of silicon material, and by doping of N-type or P-type doping concentration, like decrease the doping, the piezo coefficient is enhanced. It's like a sensitivity will be automatically enhanced of the device. So further that the gate all round field effect transistor used on the cantilever beam to tune the piezoresistivity. So in the gate all round device, the channel is doped P type and source and drain is doped N type. So here is the channel form on the interface of oxide or P type doping. So due to forming of channel near the interface, the lot of scattering happen in that. So in this device suffer a lot of electronics noise and thermal reliability. Therefore, further the junctionless device is introduced. In that there is no junction form. It's mean it's work on the bulk conduction mechanism. So whole device is doped in a single doping concentration, and so it's normally on device. So we can turn off this device by applying the gate voltage, negative gate voltage. So here we can see the gauge factor tuned by gate voltage below the threshold voltage and above the threshold voltage. We have see the lot of change in the gauge factor. So in this work, I have proposed the junctionless, using the junctionless device on a diaphragm for a various environmental condition in the sensing application. So first, I start with the device fabrication. So in that, we have fabricated the device using the SY vapor. So in the top layer, we have doped the moderate doping around 6.7 into 10 to power 18 per centimeter cube, and that layer convert in the fin by a deep reactive ionizing process. After that, this fin converted in the twin nanowire by wet oxidation process and etching process. So further, this twin nanowire to oxidize for gate oxide, and after that we deposit the polysilicon by using the LPCD mode method, and after that anneal that, and that doped with a boron, heavily doped for a gate electrode, and after that we deposit the aluminum as a contact pad to probe the device, and further we passivate the device using the silicon nitride around 1 micrometer, and so in that device we achieve the 120 nanometer channel length and 40 nanometer diameter or 4 nanometer of oxide thickness. So after passivation, we just again use the deep reactive ion etching process to open the diaphragm from backside etching of the substrate. It's this diaphragm around we have opened the 200 micrometer diameter. So further we characterize this device using the probe station and apply the pressure on the diaphragm. And also we characterize with a temperature variation like 20 degrees to 80 degree Celsius temperature. And after characterization of device, we calibrate this device on a simulation platform using the potential deformation and strain effect and density of a state and multi-electron mobility model on a TCAD simulator. So we can see in this result, when we increase the temperature, the current is increased in a both condition below the threshold voltage and above the threshold voltage. But below the threshold voltage, the current is increment is large compared to above the threshold voltage, because of in the below the threshold voltage, the intrinsic carrier concentration is also increased with the temperature. And the junctionless devices work on the bulk conduction mechanism. That's the reason the current is increased with the temperature. But in an inversion mode device, it's not an increase, it's a decrease with the temperature. So just opposite phenomena with the temperature in both device. So further we measure the change of drain current with the mechanical stress. So we can see when increase the stress, the current change of current is increased. But again, we can see above the threshold voltage and at threshold voltage, the change is current is the vary. So at the threshold voltage, it's a change is higher compared to at the threshold voltage. We can see also below the threshold voltage, it's a change is large, because here we tune the gate voltage, we decrease the gate voltage, the channel formation is the decrease, resultant of the change of current is get with the large. So further we investigate with the impact of temperature. So we can see when increase the temperature, the slight change of current is decreased, but below the threshold voltage, it's a quite large decreasement. Why? Because in above the threshold and at the threshold up to its intrinsic and phonon scattering effect is happen. But below the threshold voltage, one additional scattering effect, that is the surface roughness. So why in additional? Because in a junctionless device below the threshold voltage, along the gate is the electric field high. So there is the surface scattering is more. That's the reason with the increasing the temperature, the change of current is decreased. So in this this graph, you can see the gauge factor we have tuned by applying the low gate bias. So it's almost 4 times higher compared to on condition in a subthreshold region. And the slight decrement also in gauge factor with the temperature. So now I'm going to conclude my work. So in that, first we have fabricated the junctionless twin nanowire on a circular diaphragm, and we have measured the at a various temperature and tuning the gate voltage. So we tune the gauge factor. So here we get the 4 times higher in on condition in a subthreshold region compared to on condition. And also study the temperature impact from 20 degrees Celsius to 80 degrees Celsius on a tunable piezoresistive sensitivity. So we have observed that 4.5% the gauge factor is decreased in on condition due to impurity and phonon scattering. However, in a subthreshold region, it's almost 3 times is a decrease due to extra surface scattering. So we can say the junctionless device, it may be emerging sensing piezoresistive device in a NEMS pressure sensor, because we can fabricate the in a nanometer scale. And in an upcoming top technology node, it's maybe possible you can use. So these references we have used for writing the paper or during the work. So I would like to acknowledge also for funding. So DRDO, SERB, and ARC India, Australia Research Corporation Hub for the funding to provide this work, and for traveling grant to attend this conference. IRD, IIT Delhi, and Sensor 2023. So thank you for your attention.